So now we want to prove this lemma, which last time we showed that this actually implies the Pippinger theorem about the hypergraph matching, and then we also checked that so this implies this Pippinger theorem about hypergraph matching, and then we also checked that this implies the Eridish-Hanani conjecture, which is about the approximate decomposition of a complete K-uniform hypergraph into complete K-uniform hypergraph with a smaller number of vertices. So what was this again? So let's recall. We have a hypergraph H, which is almost regular and then has small codegree. Then this almost regular, how close to being regular or small codegree are measured by delta 0. And this this asserts that given this whole number, there exists certain thresholds, say delta prime and d prime, so that as long as delta 0 is smaller than delta prime, and then d is bigger than d prime, then, so this is some threshold, some function depending on this pole. As long as that holds, the following holds. So if it says that if H is sufficiently close to regular, and then all the codegrees are sufficiently small compared to its degree, then we can find the set of edges such that the number of edges is roughly alpha n over k. This is error parameter. And once you delete all the vertices inside of the selected edges, the remaining number of remaining vertices is roughly n times e to the negative alpha. And once we delete all the vertices and then consider the hypergraph induced by the remaining vertices, then all vertices except small number of them have a correct degree d times e to the minus alpha times k minus 1, and with some error parameter delta 1, which we can choose on ourselves. So now we want to prove this. So first, to make the computation easier, we choose several numbers, 0.1 to 0.36, such that this hierarchy of numbers hold. So this is capital K, this is small k. So what it means is that the statement is that for given this, we should be able to find this. That's what statement says. So for given this, we choose a number which is much smaller than this, but still positive. And this relation is implicit, but if you look into the proof, then you can actually specify what exactly the relation that we want. But as long as this relation holds and we choose some positive number. And for given this, we also choose delta 0.5 accordingly. And as so on, we choose next one, given all the previous one, and we choose next one given the previous one, and we choose, given this, we choose this to be smaller than that. So, there are no further relation here, so we can actually, these two are below that certain threshold satisfying this relation. It can be any, d can be bigger than, any bigger number bigger than the threshold, and delta 0 can be any number smaller than that. But we just want to show the existence of one such choice, so we assume that we fixed. And we let m prime be a subset of edges of H obtained by picking each edge of H at random. independently at random with probability P, and P is alpha over D. So for each edge, we flip a coin which comes up with head with probability P, and then which comes up with a tail with probability O minus P. If it is head, then we add this to M prime. If it is tail, we don't add. And now we will show that the three conditions, M1 to M3, holds with positive probability with this M prime. So we want to check three things. First, the number of edges chosen is close to this number, and then the number of vertices not covered by M prime is close to this number. And then once we deleted all the vertices inside of an edge in M prime, then in this hypergraph, almost all vertices has a correct degree. So first we show M1. So what's the condition that we have? We have this H1 and H2. Almost all vertices have the same correct degree. And then even if some vertices have a wrong degree, that degree is not too high. So H1 and H2 implies that the number of edges in H is 1 plus minus 0. Delta sub 0.1 times don over k. See here, you can kind of see why we make this number. So number of edges in H is actually the same as 1 over k times summation of degree. And by H1, at most this many vertices have degree 1 plus minus delta 0 d. And then at most this many vertices has a degree at most k times d. Then you can actually show that number of edges is at most 1 plus minus say k delta 0. Let's just say this k is bigger than 1, so let's say 10k delta 0 dn over k. You can actually prove this. But every time this number gets uglier every time we proceed as this computation, which is not so pleasant to see. So we just simply replace this. So this is still true as long as delta times 0.1 times k over k and compared to delta 0 if this relation holds. But we said that implicitly there are certain relations has to be hold. There are more than one relation that should be encapsulated in here, but only finitely many. One of them is, for example, here. But which we already assume, and we decided to not to explicitly write. So we just get this because we know this. So now we have give me a moment. We have this. So now what we want to do, we want to compute to show M1, we want to compute the expectation of this and then show that it is concentrated by using second moment method. For that, we have to compute the expectation and variance. What's the expectation of the size of M prime? Is that each of these edges are there with probability P. So P is, alpha over T. So this is some number between this. So again, if we write it this way, then it's at least this and most this. So, and what's the variance? Again, this m prime, the size of m prime is summation of indicator variable, where each edge is chosen or not. And these indicator variables are all mutually independent. Then for indicator variable, we know the variance. And then if they are all all independent, then this is simply the summation of all variance of indicator variable, which is p times 1 minus p. And then there are number of edges many. So this is at most 1 plus, say, give me a moment. Let me. 1 plus delta 0 times delta 0.1. Times alpha n over k. Because this 1 minus p is just number smaller than 1. So it's at most size of this. So we get this upper bound. So now use Chebyshev. We have the probability that the m prime is off by delta sub 0.2 times alpha n over k is, so this is same as the probability that we know that this is the expectation. So that's at least the probability that the m prime is within mu plus minus 0. Let's say half times delta sub 0.2 times alpha n k. You can actually show that it's 1 minus, say, 4 delta square 0.2 alpha n over k. Here, I forgot to mention, we assume that d is sufficiently smaller than anything else here. And we know that the d is at most n minus 1 choose k minus 1, because this is a degree. And then we are considering k uniform hypergraph. So that means n is automatically bigger than, say, n d to the 1 over k minus 1. This automatically ensures that the 1 over n is much smaller than anything in here. So here n is big, and then rest of them are negligible compared to n. It's so n is big. That means even if you multiply this and then subtract it, then this is still big. So when I say this is still big, you can actually figure out the relationship that say 1 over n is smaller than delta 0.2 square alpha over k 100. So this relationship is actually encapsulated in here again. So because of that, we can actually show that this happens with probability at least 0.99. So M1 holds with probability at least 0.99. Similar way, we will show that each of M1, M2, M3 holds with probability at least 0.99. And now we show M2. So what was M2 again? So we want to show that the number of vertices which are not covered by M has size this. So again, our strategy is that for each vertex, we consider the indicator variable, and then whose summation actually measures the size of V prime. So let Ix be the indicator variable of x belonging to V prime. So meaning that the Ix is 1 or 0, 1 if x is in V prime, otherwise if it belongs to an edge chosen, then it is 0. Then this B prime is summation of this indicator random variable. So now what do we know? We know there are two types of vertices. Vertices with a correct degree, vertices that could have a wrong degree. So we give name. We say that x is good if it has, so if I just write this degree without any subscript, that is a degree of x in H. So if this holds, then it's good, and if not, it's other bad. We know that even if the vertex is bad, we know the maximum degree is bounded by some constant times d. And if x is good, then we actually can measure the expectation of this indicator random variable, which is a probability that it's not covered. When x is not covered by any edges in M and end up being V prime, we consider all the edges containing this. And if none of them is chosen by M prime, then it survives, and then this indicator random variable becomes 1. And those events are independent, so this is nothing but the probability that all those degree of x many edges not chosen, which is for the good vertices, we know the degree. So we know this alpha over d is roughly e to the minus alpha. By using that, you can actually make sure that this is e to the negative alpha times 1 plus minus delta sub 0.1. So this again, observe all the error term. Here, because d is also very large, the error term coming from between this and 1 minus alpha over d to the d are negligible, which is, in terms of the capital D. Anyway, so we get this. And if x is bad, then obviously the expectation of Ix is between 0 and 1. We don't really need to optimize this value. We don't need to actually obtain the optimal value for this, because there are only small number of bad vertices. So the expected size of B prime is what? Give me a moment. This times the number of good vertices, which is 1 plus minus 0. Delta sub 0 n plus minus the bad one. Bad one could have expectation 0 and 1, so you get this. Then that's n times e to the negative alpha times 1 plus minus delta sub 0.2. Again, we made the error term gets bigger. Now what do we have to do? Again, our goal is to use second moment method to show that this is close to this expectation with high probability. For that, we need to consider the variance of B. So, in order to find the variance, we need to consider the covariance. Again, the covariance of these indicator random variables are easier to consider. So, you have x and y, different vertices. Then when does this become 1? This become 1 if both of them are in B prime, meaning that if you consider all the edges containing them, they are not chosen, they are never chosen. But one of the things is that there could be some edges containing both of them. So how many? So if 1, 2, 3, 4, 5, 6, all 6 edges are not chosen, then x, y survive, and then that's when this becomes 1. Which happens exactly when all the degree of x many, 1, 2, 3, 4 many are not chosen, and all degree of y many are not chosen. But these are counted twice, so we subtract the co-degree. So this measures this is exactly the number of edges that contains either x or y. So none of the such edges are chosen, then x, y both survives. And for each one, if we consider just this expectation, then they survive with as long as no edges containing x is chosen and no edges containing y is chosen, so which are just simply multiplication of these two. So this is nothing but 1 minus p dx plus degree of x plus degree of y, and 1 minus p minus co-degree, the number of edges containing both of them, minus 1. And this part is simply smaller than 1, so this is, you just delete this and then you put this as a upper bound, and that's 1 minus alpha over d to d minus delta 0 d, because this degree, co-degree, we know that it's smaller than delta 0 d. So because there is minus here, if you want to get the upper bound, you take the largest possible number there. Then again, this minus 1, we can actually show that this is smaller than delta sub 0.1. Again, this is something like alpha times delta 0 and a bit more, but obviously that's smaller than delta times 0.1. Hence, now we know the covariance, so we can try to figure out its variance. Bound its variance. Again, you add all the variance of indicator random variable, and then add the covariance. And again, each variance of indicator random variable is p minus 1 minus p, which is smaller than p. So this part is actually smaller than expectation of this. Because if you sum over all the things with the probability, then that's exactly the expectation. So I wrote this, but let's say p prime. It's different from the previous p, but anyway, so we have an upper bound here, plus, and what's this? For all x, y different, we have this upper bound on covariance. So this is 1 plus minus this. So we know that this is some linear vector. And then this part is 0.1, delta sub 0.1 times n squared, which is smaller than or equal to delta sum 0.2 times expectation of size of b prime square. Because this is roughly linear, some constant times linear, and then this is quadratic, but so this is negligible as n is much bigger than any other things here. So this is at most 2 times delta point sub 0.1 n squared. But because of, this is linear, so this is some constant times n squared. But the delta sub 0.1 is much smaller than delta sub 0.2. So we get this inequality. Now that's the, so as before, as long as we have the variance is much smaller than the square of the expectation times very small constant, then we can apply the Chebyshev. By applying Chebyshev, we can actually show that the probability that b prime is, off from its expectation is it's at least, it's not too far from its expectation, is 0.99. Again, for this to happen, we can actually figure out the relationship between these two. Probably, 0.03 over 100 is, say over 1000, and delta sub 0.2 is much smaller than that, then this would hold. Anyway, so we can actually show this. So we conclude that M2 also holds with probability at least 0.99. Now we need to show M3. So we will prove M3 holds with probability at least 0.99 in the next video.